Somewhere inside a research facility in Tennessee, there's a quantum computer running right now that has no giant refrigerator, no vibration-isolated chamber, no multi-million-dollar cooling tower keeping it alive. It sits on a bench at room temperature in the same building as an ordinary supercomputer, quietly doing something physicists spent 30 years insisting was impossible without freezing matter down to a fraction of a degree above absolute zero. For decades, the entire quantum computing industry has been built on one unbreakable assumption. If you want to harness the strange power of quantum mechanics, you have to pay for it in cold, in space, in complexity, and in cost. That assumption just quietly broke. And once you understand exactly how it broke and what it's already being used for right now, you'll understand why this isn't just another incremental lab result. It's a fundamental rewrite of who gets to use this technology at all. To understand why this matters so much, you first have to understand just how absurd the infrastructure behind today's leading quantum computers actually is. When you hear about Google's Willow chip or IBM's newest superconducting processors setting records for error correction and computational speed, what you're not usually told is what it takes just to keep those chips alive long enough to run a single calculation. These systems have to be cooled to temperatures colder than the vacuum of deep space, just a few thousandths of a degree above absolute zero, using a piece of equipment called a dilution refrigerator. That refrigerator doesn't run on ordinary coolant. It depends on a rare, almost impossibly scarce mixture of two isotopes of helium, one of which, helium-3, barely exists in nature at all, and is produced mostly as a byproduct of nuclear weapons programs, decaying over decades. The refrigerator itself looks like an enormous gold-plated chandelier of pipes and shielding, often standing taller than a person, housed inside a specially built, vibration-isolated room, wired into a support infrastructure that functions less like a computer and more like a small particle physics laboratory. That's before you even get to the electronics needed to control and read out the qubits, the specialized wiring that has to survive the temperature gradient from room temperature down to near zero, and the sheer physical footprint required to house it all. In other words, a quantum computer today isn't really a chip you plug in. It's a building. And for 30 years, if you wanted access to quantum computing, you needed access to that building, with that budget, and that infrastructure. Full stop, no exceptions. That single constraint has quietly shaped the entire direction of the quantum computing industry, often in ways most people never think about. It's why quantum computers live inside a handful of specialized facilities owned by Google, IBM, and a small number of national laboratories, rather than sitting on a shelf the way a graphics card does. It's why quantum computing has, until very recently, been something you access remotely through a cloud service rather than something you actually own and operate yourself. And it's why an entire category of potential applications, anything requiring quantum processing out in the field, on a satellite, on a factory floor, on a military vehicle, or embedded directly inside an existing supercomputer without ripping out the walls to install new refrigeration, has simply been off the table. Not because the algorithms don't exist, but because the physical infrastructure to run them anywhere except inside a specialized lab has never existed. That's the wall this story is actually about. And in the last 12 months, that wall has started to crack in at least 3 genuinely different, independently verified ways, each one attacking the cooling problem from a completely different angle of physics. Let's start with the most dramatic development, because it happened so recently that most of the world hasn't even had time to process it yet. On July 15th of 2026, physicists announced they had built what they're calling the first true room temperature quantum material. Not a theoretical proposal, not a simulation, but an actual, physical, tested device sitting on a chip. Rather than searching the natural world for some rare substance that happens to hold onto its quantum properties without deep cooling, the research team simply built one from scratch. They took a thin film of gold, deposited it onto a glass chip, and then used a focused beam of ions to carve hundreds of microscopic slits into that gold layer, each one engineered to behave like an artificial atom. On their own, those tiny structures don't mean much, but arranged together in a precise, repeating pattern, they form something the researchers call a quantum plasmonic metacrystal. A crystal with no natural counterpart anywhere on Earth, thinner than a single strand of human hair, and yet capable of doing something genuinely remarkable. When light passes through it, the crystal acts as what scientists describe as a quantum statistical filter, selectively transmitting and routing distinct quantum states while preserving the delicate coherence those states depend on to carry information. And they tested the entire thing, start to finish, at ordinary room temperature, using nothing more exotic than a laser-based optical setup on a lab bench. One of the researchers involved in this class of work put it simply: the material itself isn't new in any exotic chemical sense. What's new is the specific way it was engineered and used, unlocking a property that had been hiding in plain sight the entire time. It's an early result, and it isn't a complete quantum computer sitting ready to run programs tomorrow. but it directly attacks the single biggest historical barrier in quantum materials science, and it does so with a design principle general enough that researchers are already describing it as a template other teams can adapt and build on. If that result feels almost too abstract to picture, the second major development from the same window of time is easier to visualize, and it comes from one of the most respected engineering programs in the world. In May of 2026, a team at Stanford University, led by material scientist Jennifer Dayan, demonstrated something that had never been achieved before outside of a deep-cooled lab environment: genuine quantum entanglement between a photon of light and an electron, occurring at room temperature on a chip built using materials compatible with standard silicon manufacturing. The method they used sounds almost like something out of speculative fiction, and yet it's fully documented, peer-reviewed physics. The team used a specially engineered form of light, sometimes called twisted light, which carries a subtle rotational property as it travels, and combined it with an ultra-thin material called molybdenum diselenide, arranged into silicon nanostructures capable of holding what physicists call Valley states. Essentially, distinct electronic pathways within the material that can be individually addressed and manipulated. By carefully tuning how the twisted light interacted with these Valley states, the Stanford team managed to entangle a photon and an electron without ever needing to cool the system down anywhere close to the extreme temperatures normally required to protect such a fragile quantum connection from being destroyed by ordinary thermal noise. It's crucial to be precise about what this actually is and isn't, because it would be easy to overstate it. This is not, on its own, a working quantum computer you could sit down and run a program on tomorrow. What it is, and why physicists are excited about it, is a foundational building block, an entanglement source, a kind of quantum to classical interface that could eventually feed into room temperature quantum. Computers, quantum communication networks, and the broader, still emerging vision researchers call the quantum internet. Building a car engine is not the same as building a car, but you cannot build the car without first solving the engine, and that's precisely the category of problem this Stanford result solves. Now here's where the story stops being purely theoretical and starts becoming something you can actually point to physically in the real world, because while physicists in California and elsewhere have been proving that room temperature quantum coherence is possible in principle, a small company on the other side of the planet has already been quietly shipping and installing working room temperature quantum processors into real government and research facilities for over a year. The company is called Quantum Brilliance, founded in Australia in 2019 with its main development facility based in Stuttgart, Germany, and its approach to this entire problem is almost elegantly simple once you understand it. Instead of superconducting circuits or trapped ions or photons bouncing through optical fiber, Quantum Brilliance builds its quantum processors out of synthetic diamond, using a naturally occurring defect inside the crystal lattice called a nitrogen vacancy center, or NV center for short. Here's the beautiful part of the physics, and it's worth slowing down to actually explain it, because it's the whole reason this approach works at all. Diamond is one of the hardest, most rigid materials known to exist. At room temperature, there simply isn't enough ambient thermal energy available to generate the kind of atomic vibrations that would normally disturb and destroy a fragile quantum state. On top of that, diamond can be manufactured to an extraordinarily high level of purity, which all but eliminates the stray electromagnetic noise that typically corrupts quantum information in other materials. Put those two properties together and something genuinely strange happens. The nitrogen vacancy centers sitting inside that diamond lattice experience an environment at ordinary room temperature that is functionally equivalent to the near absolute zero conditions other quantum computing platforms need enormous refrigerators to achieve. No dilution refrigerator, no specialized laser cooling system, no vacuum chamber, just a small, solid chunk of engineered diamond, sitting quietly at the same temperature as the room around it, holding on to genuine quantum information. The recognition for this approach hasn't been limited to academic physics journals either. In 2025, Quantum Brilliance was named one of Time magazine's top 100 inventions of the year, placed in the same list alongside major technology players like NVIDIA and Microsoft. A remarkable achievement for a company most people outside the quantum computing world have never heard of. And unlike so many of the flashier, headline-grabbing quantum announcements that turn out to be single laboratory demonstrations, Quantum Brilliance's diamond-based processors are already physically installed and running inside real operating research institutions around the world. The company's systems have been deployed at the Pawsey Supercomputing Center in Australia and at the Fraunhofer Institute in Germany, both integrating these room temperature quantum accelerators directly alongside existing classical supercomputing infrastructure rather than requiring an entirely separate, specially built facility. Then, in September of 2025, the technology crossed the Pacific and landed at one of the most important computing institutions in the United States, Oak Ridge National Laboratory, operated by the U.S. Department of Energy. There, researchers installed a cluster of 3 of Quantum Brilliance's diamond-based quantum development kits, nicknamed Qual, combining 3 parallel quantum processing units for a modest total of 6 qubits. 6 qubits is, by the standards of Google's or IBM's superconducting processors, an almost laughably small number. Those systems are pushing past 100 qubits and climbing. But the number of qubits was never really the point of this deployment. The point was that Oak Ridge, one of the most sophisticated high-performance computing centers on Earth, was able to install a working quantum processor as a commercial, off-the-shelf product sitting inside its existing facility without needing to build a single new dilution refrigerator or dig out a specially isolated room to house it in. That is precisely the kind of quiet, unglamorous milestone that changes an entire industry's trajectory, even when it doesn't generate the same viral headlines as a flashy new speed record. And Quantum Brilliance isn't slowing down with these early deployments. Reporting from March of 2026 describes the company actively expanding its diamond fabrication process deeper into the established global semiconductor supply chain, working alongside IMEC, one of the world's leading semiconductor research organizations based in Belgium, to figure out how to manufacture these diamond quantum chips at a scale and consistency that mirrors how the rest of the chip industry already builds conventional processors. Perhaps even more telling for where this technology is actually headed, the company has entered into a government-backed partnership in Germany, specifically aimed at demonstrating, by 2027, a compact quantum computer capable of functioning in genuinely real-world field conditions, not a climate-controlled lab, but places like mobile command centers or remote installations, environments where hauling in a multi-ton cryogenic refrigeration system was never going to be a realistic option in the first place. Think about what that actually implies for a moment. A quantum processor, small enough, rugged enough, and independent enough from specialized infrastructure that it could theoretically be mounted in a vehicle, carried into a disaster response zone, or bolted onto a satellite orbiting the Earth. All places where the extreme cooling requirements of a traditional superconducting quantum computer would make deployment physically impossible, no matter how much money you were willing to spend. It's worth pausing here and being scrupulously honest about where this technology genuinely stands today, because overselling it would do a disservice to just how impressive the real grounded story already is. Diamond-based room temperature quantum processors are not, right now in the middle of 2026, outperforming the raw computational power of cryogenically cooled, superconducting or trapped ion systems built by companies like Google, IBM, IonQ, or Quantinuum. Those systems are pursuing higher qubit counts and, in some cases, are already demonstrating specific tasks where quantum hardware clearly outperforms classical computers on narrow, specialized problems. A 6-qubit diamond cluster sitting at Oak Ridge is not today solving problems that a 100-qubit superconducting processor cannot. What Quantum Brilliance and companies like it are betting on instead is a fundamentally different value proposition, one that has nothing to do with winning a raw horsepower contest and everything to do with winning the deployment contest. Their argument, and it's a compelling one once you see the deployment map laid out in front of you, is that a quantum processor, which can be installed inside an existing supercomputing facility without a single structural modification, or eventually mounted onto a moving vehicle, a remote sensor station, or an orbiting satellite, opens up an entirely different category of use cases that raw qubit count alone will never unlock, no matter how impressive the number gets. It's the same logic that eventually made smartphones more transformative to daily life than early supercomputers. Even though any serious 1990s mainframe could still, on paper, outcalculate a modern phone on certain narrow benchmarks. Deployability, accessibility, and integration with existing infrastructure can, over time, matter more than raw peak performance. And that's precisely the bet this entire category of room temperature quantum hardware is making. China, predictably, is not sitting on the sidelines of this particular race either, and its approach reveals just how many different physical paths researchers around the world are simultaneously exploring toward the same destination. A Beijing-based company called QBoson has built its entire commercial identity around a room temperature quantum hardware platform that requires no cryogenic cooling whatsoever, using photonic rather than diamond-based architecture. The company broke ground on a dedicated manufacturing facility for this photonic hardware in August of 2025, and by April of 2026, it had closed a funding round worth roughly $145 million, one of the largest single quantum computing investments in Chinese corporate history, led by state-linked financial institutions, including Beijing Financial Holdings Groups and ICBC Capital. It's important to be precise about exactly what QBoson has built, because the marketing language around quantum technology can sometimes blur an important technical distinction. QBoson systems are what's known as coherent Ising machines, a specialized class of hardware. purpose-built to solve certain optimization problems extremely efficiently rather than universal. General-purpose quantum computers capable of running any arbitrary quantum algorithm the way IBM's or Google's superconducting processors are designed to do. That distinction matters, but it doesn't diminish the broader point this story is really about. Whether you're looking at a diamond-based general-purpose processor from an Australian-German company, a photonic optimization machine from a Chinese startup, or an experimental gold metacrystal built in an American physics lab, you're looking at the same underlying trend playing out simultaneously across multiple continents and multiple completely different branches of physics. Engineers and researchers everywhere have independently urged on the conclusion that the extreme cooling requirement holding quantum computing hostage inside specialized facilities isn't actually an unbreakable law of nature. It's an engineering choice, born out of which particular physical systems happen to be the easiest ones to demonstrate quantum effects in decades ago. And choices, unlike laws of physics, can eventually be replaced. There's a subtler engineering trend worth folding into this story too, because it shows that even inside the traditional, cryogenically cooled quantum computing world, the direction of travel is unmistakably towards shrinking the infrastructure burden rather than expanding it. A Canadian startup called Cubic has developed a specialized cryogenic amplifier, a small component used to boost and measure the faint electronic signals coming out of a quantum processor that reportedly reduces the heat generated by that single component by a factor of roughly 10,000 compared to previous designs, with a potential commercial launch targeted for sometime in 2026. So, stepping back from all of these individual threads and looking at the bigger picture they collectively paint, what does it actually mean, in practical terms, that quantum chips no longer strictly require a data center to function? It means the earliest, most tentative first steps toward genuinely portable, embeddable, field-deployable quantum computing are no longer speculative fiction. They're sitting on lab benches and inside government research facilities today in the middle of 2026, actively being tested, refined, and expanded. It means a satellite could, in principle, eventually carry a genuine quantum processing unit on board without needing an onboard refrigeration system large enough to rival the rest of the spacecraft's mass budget. It means a research supercomputing center like Oak Ridge can bolt a quantum accelerator directly onto its existing infrastructure, the same way it might add a new graphics processing card, rather than commissioning an entirely separate specialized building. And it means the eventual dream of quantum computing becoming something closer to an accessible tool rather than a scarce resource locked away inside a handful of billion-dollar corporate and government laboratories has taken its first genuinely credible, physically demonstrated steps forward, rather than remaining purely a talking point in a funding pitch deck. None of this erases the very real, very impressive progress happening simultaneously on the cryogenically cooled side of the industry, where Google, IBM, and China's leading state-backed research institutions continue pushing qubit counts, error correction thresholds, and raw computational advantage forward at a genuinely remarkable pace. Both stories are true at once, unfolding side by side, often inside the very same research institutions. But it's this second story, the quiet, less flashy one about diamond chips shipping to Oak Ridge, about gold metacrystals holding on to quantum coherence on an ordinary lab bench, about photons and electrons entangling on a silicon chip at room temperature, that carries the deeper, more disruptive implication buried inside this entire field. Because for 30 years, the single biggest barrier standing between quantum computing and the rest of the world wasn't a lack of clever algorithms, or a shortage of brilliant physicists, or even a failure of ambition. It was a thermostat. And for the first time in this technology's history across at least 3 genuinely independent branches of physics developed on 3 different continents, the thermostat has finally, quietly, verifiably started to become optional.